Thanks. And thank you for inviting me here to the workshop to give this talk. I guess because it's a physics workshop in addition to a machine learning workshop, I thought I'd give a chalk talk like I used to when I was a practicing physicist. So the title is Deep Learning as a Toy Model of the 1/n expansion and renormalization. And it's a little glib. I'll get into sort of why that is. It's joint work with Boris Hannon at Texas A&M, David Schwab at CUNY and FAIR, Shoyeda at FAIR, and there's a bunch of related papers that I've written up here that I'll try to reference when I give the talk. And as a warning, all this material hasn't come out yet, or the project that we're working on hasn't come out yet. So what we're doing is very preliminary, and as a result, I'm going to end up reviewing some of the content in these previous papers, although the way in which I'll be doing it is maybe a little different that's in the literature, and I'll derive some other results that aren't in the literature, and I'll try to point the way at these previous papers when I get there. And more importantly, I hope to sort of promote a more general program that we're working on and explain what that is by way of this introduction. So, right, so the hope is to outline this program rather than give you the full explanation of what it is that the four of us have written up there are pursuing. So our goal as physicists who are entering this new field of machine learning is to really find and analyze a family of increasingly realistic toy models for deep neural networks that are rich enough to capture the important features. And I guess realistic, I am holding my notepad, but I would have used quotes for realistic and important. It's obviously up to us to decide what those mean, but the idea is to sort of develop a framework for studying models that may capture what we think deep learning is doing that's significant, and then try to understand that either theoretically or with numerical experiments. So the sort of questions that we want to answer, and these questions have came up over the course of the workshop, so I'm not saying anything new by listing these questions. I just want to sort of outline the direction that we're going to be thinking about is, one, how do we select the right architecture for our data, perhaps given something about the statistics of our data. The sort of heuristic idea here is that when we use convolutional nets, we know that there's something about translation and variance in our data. But can we make those sorts of ideas more quantitative? Can we take them further given other statistics about data? Or what is a framework for sort of developing these sorts of ideas? Similarly, can we design better activation functions? Or what's the right way to initialize activation functions? There's, again, a lot of prior work here, but sort of, is there a systematic way of sort of solving or answering these questions? And related to the things I've just said, what inductive biases or priors do our neural networks have? Perhaps if we think about neural networks in some way, we can understand directly what that prior is and compute it quantitatively. And finally, how do we learn, or how do these networks learn features, or are they just memorizing data? Is there some lazy learning versus feature learning phase transition, and what could we say about that? So I'm not going to answer any of these questions, or I might answer one of them, but I hope that this sort of framework will lead to being able to answer these sorts of questions once it's sort of completed. But I just wanted to sort of guide what I'm talking about. Sure. Cool. So the sort of tools that I'm going to be using is the large N expansion and perturbation theory. And renormalization group. And critical theory. So really, all these ideas coming from where we have some parameter that gets very large and things simplify. So what I mean by that explicitly, if we have some function that we care about, say f of x, we can use perturbation theory to study f of x plus epsilon for epsilon small by Taylor expanding. If we instead have some really large parameter so that epsilon is 1/n, then the limit where epsilon goes to 0 is the same limit where n goes to infinity. And just like we can use perturbation theory to study simple systems that we understand and perturb them away using a small perturbation, we can also study certain systems where, say, the degrees of freedom get very large, and we can study then a perturbative expansion as we move away from the limit where, say, the degrees of freedom are infinite. And this, I'll point out along the way, but this should sound familiar either if you're familiar with mean field theory or the thermodynamic limit. These are the same sorts of ideas, and the simplifications occur for reasons that you might understand in those contexts. So in particular, the limit that we're considering is the limit of infinitely wide neural networks. So the number of parameters is going to infinity, and it's going to infinity in some sense at each layer. The depth will not be constrained in my talk, so it can be whatever it wants to be. So this is useful because it yields an analytically solvable limit. In which case there's an identification of infinite width neural networks with Gaussian processes. And that was, I believe, first analyzed in this old paper from the 90s by Neal for single layer networks, and then was extended in this paper in 2017 for deep networks. And there's a related, sure. The reason this is interesting is because in this limit, the Gaussian process yields a prior for the network outputs, which can be used for Bayesian inference, which was first outlined in this paper by Williams and also addressed in this paper by Lee and Bari. So given this relationship, which I'm going to go over in a second, we can then try and analyze the limit as we allow the network widths to be finite again. And this was first pointed out in a very recent and amazing paper by Shoyeda, one of my collaborators, and really forms the backbone of everything that I want to talk about in that it provides a systematic way of understanding how to correct this infinite width assumption, which in some sense is unrealistic, understand what the errors are, and to start computing quantities that we might care about for finite networks. And I'll start explaining what those quantities are when I get into the details of this. But the sort of things that we might be able to do is understand corrections to the infinite Gaussian process Bayesian inference, or corrections to how we do kernel learning when we don't have a Gaussian process. We have something that's like, I don't know if it has a name in this field, but it's essentially a non-Gaussian process. The distribution of activations is no longer Gaussian, and so it allows them to perhaps have more interesting correlations than simply a two-point function. Okay, so that's sort of the setup. Now I'm going to go into some details and calculations. I guess let me pause if there's any questions. It was very schematic, I know, but at least questions about what I'm trying to talk about. Cool. So we're going to start by talking about neural networks and the infinite width limit. So as I said before, this is sort of a mean field theory thermodynamic limit. As a physicist, I would say that the interactions are turned off, leading to a Gaussian free field theory or a Gaussian process. I'll explain. There is actually a sense in which it's meaningful to talk about interactions, but I'm only saying that as a way of sort of winking at people that might be familiar from physics. I'm going to focus on MLPs to start, but there's a huge industry. A lot of these authors, I haven't listed the papers, of extending these results for things that are not just multi-layer perceptrons. So everything I'm going to say can be extended to more interesting architectures, but sort of the crux of the interesting behavior occurs for MLPs. And the parameters I'm going to represent as biases at layer L. So this is the ith bias at layer L, and then there's weights also at layer L. and L will go from 1 to capital L. And so we can define this sort of network in the following way. So the pre-activation Z at the first layer, and X will be my input, is equal to the bias plus the weights acting on the input, as you're all very familiar with. And then the pre-activation at layer L is defined recursively in the following way. So we have a bias at layer L plus a sum over the weights acting on the activations like so. As I said, L here will go from 2 to capital L, goes from 1 to NL. So this should all be very familiar. In some sense, I'm just establishing my notation here. And at initialization, we have a random network. So we're going to sample our biases and our weights from Gaussian distribution, and with correlations with zero mean and correlations. So for the bias, they will have some covariance. So it's diagonal in neural indices and independent on independent at each layer, and then there's some covariance at layer L for the bias. Similarly, we'll define the weights the same way. Oops. So diagonal in weight space and independent on each layer. And then there's some CW, some covariance for the weights, and then we'll also divide by the width of the layer. And we do this so that we'll have a nice limit when eventually, in 1 second, I take n to infinity. So this is sort of a standard, in some sense, depending on what you put for CW, a standard idea for how we initialize. We initialize according to the width of the previous layer. So the large n limit, can everybody see if I write down here? It's good? Okay, so the large n limit is going to be defined where we're going to let n1 to nl minus 1, capital L minus 1, is going to equal some n. For convenience, I don't actually have to do this, but it just simplifies notation for this talk, and that's going to be much greater than 1. This also means, however, that the input and output dimensions can stay finite. So we can still use this analysis, and in fact, not only use this analysis, we can practically use this in terms of doing inference on a practical data set that has some finite input dimension and has a finite number of output, say, classification categories. So it's just the hidden layers in the middle that we're taking to be very large. And so the point of, or in this limit, we can define the two-point function, or the kernel, which has indices for in weight space and in data space, and that's defined to be the expectation value of the pre-activations. So this is, say, the kernel at layer L. So it's defined to be the expectation value of the pre-activations at layer L. The correlation function. The correlation between two pre-activations at layer L on different inputs. And well, it's also easy to see. So first, it's easy to see that the one-point functions on a single input will vanish. So the first non-trivial object is this object k, which is this two-point function between pre-activations. And so when you do the analysis, and actually I'll reproduce it, you find that at layer L, all the higher point correlation functions can be expressed in terms of the kernel. And in other words, the statistics of these z's are Gaussian, or you have a Gaussian process. And this happens at infinite width. So yeah, does this make sense so far? Or is anyone, yeah, go.
I just want to understand your notation. So the biases are delta correlated, right? So there's no, only diagonal elements are there, right? In both domains, in both the weights and the bias.
Yeah.
So nothing is correlated to anything.
That's right.
Okay.
Correct. This is what we normally do when we.
This is just a scale then, right? CBL is just the scale.
This is a scale. This is a.
CBL is the value of each B. At the layer L.
Typically, yeah.
Okay, that's what.
Yeah, exactly. Exactly. And similar statements about this. I'm putting an n here to make the large n limit nice. This is what we normally do, right? Okay. Other. Yep.
In which way is it different from the NTK?
Well, I haven't. So this is just defining a large n limit.
It's the same because there's two ways you can take it. You mentioned mean field. Mean field would be, instead of putting the n there, you could put the 1 over square root of n instead in front of the sum.
Well,
mean field is 1 over n.
Well, in the way I'm thinking about it, it doesn't matter where I put the n. That's not what I mean. Mean field is just the fact that n is large.
No, because, sorry, I want to clarify, because whether you put 1 over n or 1 over square root of n makes a big difference. In one case, you get the mean, what has no big, called the mean field limit. In the other case, you get the NTK, which is this Gaussian process, and it's quite different.
Well,
so I just want to clarify. You're doing the one where it's 1 over square root of n.
Well, so since I haven't talked about any learning yet, there doesn't make sense to talk about the NTK, right? The NTK is just some object that you could define using these variables. It might have a nice limit in large n, it might not. Similarly, there's some object which is the two-point function of the pre-activations. This is a different object than the NTK. This is the Gaussian process kernel, right? They're used for different things. And we can talk about whether they have a sensible limit depending on where we put these n's. And so, like, there's no. Does that make sense?
No, but W are Gaussian, right?
Yeah.
Okay, so then 1 over square root of n is the right.
I think I don't want to get into the details of the NTK because this talk's not about the
N. But you could decide to do something else.
No, for Gaussian, no.
For Gaussian, no, I understand. Thank you. I understand it very well. But it's just, I'm just trying to clarify. There will be talks about NTK.
Sure.
I think that we introduced exactly the same object. So I just want to know whether.
Well, the NTK, in some sense, this kernel is about Bayesian inference, and the NTK is about learning. I'm not talking about learning during this talk, but for the NTK, there's a different weight normalization that's typically used, but you don't have to do that. You just get n's in other place if you want a nice limit, and so we can work that out or not. This might not be what's typically used for the NTK weights, but I'm not talking about the NTK during this talk. We can talk about the relationship after, but I think this should just be sensible. This is just notation, and then when we try to take the limit, if we get a sensible answer, then it's sensible. If not, maybe we move the n's around. That's.
But I want to make a comment with respect to you. 1 over square root of n here, which is the n, where you use the Gaussian, you want to use the CMT. But if you take something else, you could perfectly have a random variable there and just use the law of large number with 1 over n. It's a different. It's a different limit. Right? There's no.
For Gaussian, this is the right thing. That's
Okay, so. What I'm going to show next is that if we consider the pre-activations at layer L, and then we ask what they look like at layer L plus 1, using the definition of the network, we'll get a recursion relation for this kernel. And based on how we chose the ends here, we'll be able to see that all the other correlations that are higher than just 2-point are going to vanish. So This is just like a simple one-line thing, but it's somewhat instructive to see. So we're going to, instead of considering the correlations at L, we'll consider them at L plus 1. So we want to evaluate the correlations between inputs of the next layer. We propagate to the next layer using this equation, and we get a squared. We get a square. So there's a term that relates to the bias squared, plus there's cross terms, which I'm not going to write because the weights are independent and the one-point functions vanish. And then there's the term for the WZ squared, or the W sigma squared. And since we know the weights are independent, we're going to then get a final relationship, which is that the kernel at the next layer is given by this expression. Where this is an expectation value over this kernel at layer L. So it depends on, so the kernel at the next layer for the Gaussian process depends on the kernel at the previous layer and what the scales of the correlations of the bias and the weights are. And this expression only holds at infinite n. Otherwise, there would be corrections, which I might get into if I have time at the end of my talk. And similarly, all the higher point correlation functions are just determined in terms of this object, plus things that vanish in powers of 1 over n. In fact, I can just write it. One can show that the expectation of say, z for input alpha 1 to z at input alpha m for the connected part is going to go like order 1 over n to the m over 2 minus 1. So when m is 2, we have something that's finite at large n, but for when m is when m is 4 or greater, the odd ones vanish, I should have said. So when m is 4 or greater, we're going to have these vanish at infinite n. Otherwise, there's corrections. A physicist would say that only the 2-point function is non-trivial. So what we're really doing when we compute an object like this is that we're integrating out the intermediate weights and biases and the weights and biases and intermediate activations. It's sort of akin to an RG flow, and the kernel is an effective description of the network. Basically, you get.
You also have more collectors behind those.
It's fine, unless if anyone was looking at this. The kernel is an effective description of the network. Basically, it's some probability distribution over. It gives you solving this sort of recursion would give you some probability distribution over pre-activations evaluated on certain inputs, and that distribution, the statement that it's a Gaussian process is that distribution schematically looks something like this. Oops. So the prior this is really a prior distribution over pre-activations, but the point is that if we just put some data into the network, and then what do we see at the last layer? If we compute this at layer L, or you can ask this at any layer, and use the kernel at layer L, and it says that the pre-activations will have this distribution. We didn't have to know anything about the other weights or biases or other pre-activations. We integrated them out. We have essentially an effective theory who's fully determined by, and the behavior is fully determined by what this K is.
I'm sorry for notation. You have alpha and I?
I think I wrote something correctly here. So these are data indices. And I need to put data indices. I did. So, and I've suppressed when indices are repeated. It implies a sum, so I've suppressed the explicit sum. So these are data indices.
So this is not the prior.
Sorry?
That's already the prior.
This is the prior because I haven't used any labels yet.
So alpha 1, alpha 2 are the data, and then what is ZI?
So
multiple output units or something? What is that?
Yes, or it's a sum over the. These are weight indices. So exactly. Sorry. If there's multiple output heads, this is just the sum over them. So it just says that each one is not correlated with the other one because okay. Great. So. Great. That concludes the introduction to what this Gaussian process is. Now that we have this, what I want to do is ask what are the right observables to look at. So we know that in the limit of an infinite network, there's this sort of simplifying description of what the network is. And so given this is somewhat of a UV Gaussian fixed point, we want to ask what are the relevant observables, say when we flow to the IR, or as we keep going through additional layers in the network. Yeah. So explicitly what we're going to do is solve this recursion equation in a couple of simple cases and derive some initial insights. And then after we do that, if I have time, I'm going to go on to the 1 over n corrections. So what we're going to do is consider the question of an input and a perturbed input and how they propagate through the network. How do the signals correlate as they propagate? Some of these results, but not all of them, appeared in these two papers by Poole and Schoenholtz and Gilmer. And although there'll be some differences, and I'll point them out along the way, and the way of thinking about that, this compared to them, I think is a little different. So what I want to do is define two inputs, x plus and x minus, which are perturbed around some input x0. So x plus minus is x0 plus or minus some 1/2 delta x. And the objects of interest, which I'll also define, that we want to compute are the kernel that says how how x plus and x plus correlate, or x minus and x minus. This is just using the definition of the kernel. And then there's another object, x plus minus x minus plus, which says how the two different inputs correlate. So how x plus correlates with x minus. And then, of course, one other object that I'll define is just the correlation of the initial input that we're perturbing around. And so the strategy here, and I'll only sketch the computation because some of it's involved, is that we feed x plus and x minus into the network, and then we see how the pre-activations evolve from layer to layer. And their evolution is encoded by these different kernels. And then we're going to understand what the recursion relations are for these kernels in a perturbation theory in delta x. Why is this a good set of observables? I probably have to stop erasing to fully be able to write it out. So why is this a good set of observables? Oh, sorry, before I do that, also note I'll sometimes write some capital K, here I'll put a tilde on it to try and differentiate it, which is just composing this kernel into a matrix, 2x2 matrix. Okay, so one reason is that there's a nice observable, which I'll call DL, which tells you the average distance between Z plus and Z minus at layer L. Or let me define what I mean. I didn't define Z plus and Z minus. So what I mean is Z on X plus at layer L minus Z of X minus on layer L. That quantity squared is some distance between the two perturbed images, or an image between the signals x plus and x minus, and so we can see whether they're converging or diverging. This is perhaps interesting because if you're considering some classification problem, you might expect that nearby images, say an image classification, you might expect that nearby images should converge because they're related to the same category, or you might expect that orthogonal images should not converge because they might signify something different. In high-dimensional space, you might expect, say, that images that come from or sampled from different categories might be very close to orthogonal. So it's interesting to consider how the distances between nearby signals either converge or diverge. And so we can express this observable in terms of these objects I've defined over here. So this distance is equal to k plus k minus 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 2k plus minus. Similarly, there's a related object, which I'll label R of L, which is given by k plus minus k minus minus of L. And this object is proportional to 2 times, schematically, 2 times z delta z, or the norm of, or the change in the norm of the pre-activation from layer to layer. So this is an observable that says how do nearby inputs propagate through the network, how does the difference between them change, and this says how does the norm of a signal change as it propagates through the network. So these are perhaps interesting objects to compute. They're computed from these correlations here, and so for the next part, let me just derive how we represent what these correlations are.
So is DF supposed to be a scalar or a matrix?
It's a scalar.
You need traces somewhere.
I only have, let's just take this to be, or fine, we can say at n, a layer NL, we sum over the NL. So I, put an I there, and I there. Is that better?
Trace on the next line, it's okay.
I'm defining this to be on a single input, on a single neuron. So then I don't need a trace, I think. Is that correct? It doesn't, because of the permutation symmetry at a given layer, it doesn't matter whether I focus on a sum over all of them or just one. Yeah.
And you don't consider ij in your k++, right? Z is the point.
I think that's the same question.
Yeah.
Yeah.
Singular.
Sorry?
Singular. Okay.
Yeah, I'm considering here, I'm just considering one pre-activation around. Because of the permutation symmetry, it doesn't matter. I could choose to sum over them and average. You get the same answer. I was just trying to do this for simplicity. It's an MLP, and in the middle there's nothing that signifies a particular output pre-activation from any other one. So we can just focus on one, do the large N statistics. Okay, so given that we have this, now we're going to compute these Ks. So to get some intuition, let's just consider the first layer. So we have K plus minus at layer 1. And that's going to be given by the following expression. That's going to depend on the bias covariance, the weight covariance, the norm of the centered input signal, plus or minus a term that's going to care about essentially the change in norm of the input signal between the original and the perturbed image. And the norm of the perturbation. There's a similar expression for K plus minus plus after the first layer, which has a piece that depends on the order 0 part. And a piece that depends on the norm of the perturbation. So this is just from plugging in the initial condition from the neural network and then evaluating it with that particular input x plus minus. The reason for doing this is that we see that in order to have something non-trivial, or if we were to evaluate the expression for D1, it would depend solely on the norm of the perturbation squared. So that tells us that we need, in order to see something non-trivial here, we need to solve this recursion and perturbation up to order delta x squared. Otherwise, we won't see anything useful. So the sort of thing we're going to need in order to compute this, and I'll try to go through this somewhat quickly. Is it okay if I erase this? So we're going to need to compute objects that are like the expectation of sigma z for some input alpha at layer L, and then sigma z for some input beta at layer L, and where we average that over the kernel k alpha beta at layer L. And in general, that's not going to be diagonal anymore. So the process for solving this is that we're going to need to diagonalize the kernel. So we'll define new coordinates z plus minus are equal to some coefficients cu plus minus times u plus cw plus minus w. I'm basically just saying that it's a change of basis. So we diagonalize the kernel matrix K. And switch to new coordinates u and w. And once you do this computation, you find that the eigenvalue for u, or the covariance of u, is 2k00 plus 2 times an object that I'll define in a second, or I will explain this expression in a second. And then there's a similar expression for W. And importantly, so
Sorry, what do you think?
yeah, I need to explain what these. Oh, sorry, that I can explain before I write another thing down. So I'm just defining new coordinates such that I have this kernel k plus plus, k plus minus, k minus plus, k minus minus. I want to find coordinates where it's diagonal. Those coordinates are u and w. I'm just diagonalizing a 2 by 2 matrix, and these are the eigenvectors. And so I'm just switching to these coordinates. That's all I'm doing here. And now I'm telling you that in these new coordinates, the eigenvalue of this k matrix for u is given by this expression, for w is given by this expression. I haven't defined what these deltas are yet. Let me do that. So these deltas essentially give you the first order and second order perturbations of the kernel. So k plus minus is k00 plus minus delta k plus delta delta k, and then plus delta delta k2. We need to define two of these objects. I'll explain why in a second. And then k plus minus plus is equal to k00 minus delta delta k plus delta delta k2. So there's a sign difference here, and so in order for the recursion relations to close, we need to have two of these delta delta k objects, and in the end, the dl that we care about is just equal to 4 times delta delta k. And so the whole point of this exercise, or one of, I guess, this RL also is equal to 2 delta k. So the point of this exercise is to evaluate these functions, at layer L, is to evaluate these functions at layer L, and that tells us about the observables that we want. At a particular layer, we diagonalize the kernel, and we find these new coordinates, and the eigenvalue for the u coordinate is given by this expression. The one for the w is given by this expression. Note that as we take delta x to 0, all the kernels with deltas vanish, as expected, so we just get the correlation of the original image with itself, or the original input with itself. And so the w eigenvalue is going to 0, whereas the u eigenvalue is just replicating the original kernel. And so that's sort of.
So are you assuming delta x is small with expansion delta x, or for now?
Oh, sorry, I thought I said that. I'm assuming delta x is small, and I'm doing expansion in delta x.
These delta k's and delta k's are high orders. Delta k will be small.
Yeah. So for instance, over here, this is k00, and this is delta k for layer 1. It involves just one delta x in it. So as I push this perturbation,
delta k is linear in delta x, and delta is.
That's right. And there's this is a particular ansatz for the recursion relation that holds. There's one subtlety with this change of basis. There's always a phase factor when picking the eigenvectors. You need to make sure that in the limit where delta x goes to 0, that z plus and z minus map onto z0. They should map onto what the original input signal is. So that involves perhaps a non-trivial sign based on where your normal algorithm is. But that's very important. So let me just finish outlining this procedure, and then I'll start talking about some of the results, which perhaps are more interesting. So the point of this procedure is that we can now expand the sigmas for layer L at z plus z minus by substituting in these coordinates here, and knowing that that expectation values that involve the w coordinates are going to be small in the perturbation. We can expand in a Taylor series around w, so we get some expression that's expanded around the w coordinate. so on. And then we plug this into the definition of k, and then we can evaluate the w integrals, we can evaluate the u integral, and then we can evaluate the w integrals, then we change coordinates from u back to z minus, back to z0, or we expand the difference between, because u is basically the same coordinate as z0. I guess the details, if you're interested in the details, please come and talk to me after. When the dust settles, though, we get some nice expressions. So I'm going to write them and analyze them, and that will probably take me to the end of my talk. So for delta k, we get this expression that depends on CW, delta k at the previous layer, and then the derivative of sigma prime squared. And then I'm just going to use this quick notation to mean an integral over k0, 0. Integral against the kernel with k0, 0. So we get some expression for delta k. This object here I'm going to define as chi parallel for reasons that will become clear in a second at layer L. And then for delta delta k, we get a slightly less nice expression. It depends on delta delta k at layer L. Oops. I need to include. Times the expectation of the derivative of sigma. It's layer L. And this object I'll define as chi perp, but plus then an additional piece that depends on delta k squared. And some less nice expression. So these are the objects that we wanted to compute, because dl is equal to 4 delta delta k at layer L, and rl is equal to delta k. I think it's 2 delta k at layer L. So we have some expressions for them that say that if we take these expectations with respect to some functions of our activations, then we can compute, assuming that we knew what the distance was. If we know the distance at a previous layer, then we can compute these expectations, and then we figure out what the distance is at the next layer, or the size of the norm.
So delta k2 is not.
Yeah, so delta k2 doesn't play a role in this. You need it for these equations to close. It's sort of interesting. Let me address that in the analysis, which I'm going to do right now. So this is a lot of maybe too much algebra, but now we can start to answer the questions of what happens to nearby inputs with what happens to nearby inputs. And there's a surprisingly large amount of physics lurking here, and this is sort of why I titled my talk, because I think in the end, what you end up finding is that these sort of deep networks are just providing models of the same physics that we've seen in the large N expansion, and we get all sorts of critical exponents and interesting scaling conditions, and there's a large amount of machinery that we can then start to put towards solving this problem. But before I get there, let me address this question of where the physics is here. So for start, let's consider the case where the perturbation is orthogonal to the input. So in that case, because this is delta k at layer 0, we see that expression appears here, so that vanishes. Since this equation only depends on delta k, it doesn't depend on delta delta k, the recursion for this says that this delta k stays 0, so we can drop this part, which depends on delta k squared, and just focus on this over here.
It's stable?
Sorry?
Is it stable?
Yeah. And we can talk about, there's nice ways of analyzing that, but yeah. So what we get is an expression that delta k L plus 1 is equal to delta k at L times chi L perp. And the solution to this recursion, so let's assume that this is just the same, let's make an ansatz that this is the same at each layer. So that would yield a solution, or sorry, no, that's fine. Let's make that ansatz. We'll see what that entails in a second. But if that were the case, then this distance would have the following behavior, the following exponential behavior. So the distance would go exponential in L, which is basically equal to e to the minus m perp times L, where I've defined a mass as minus the log of this chi star perp. So what we have is we have a particle that's a massive particle, and it's essentially a damped oscillator. And the distance between nearby images decay depending on this mass, which is computed according to this correlation function. So it's some natural scale that arises from your choice of your weights, your biases, your activation functions, and so on. And this, I erased the paper, but this was reported in the paper that I listed by Schoenholtz, and I think also in the paper by Poole. They noted this in the paper by Poole. They noted this recursion. They noted this, and in the paper by Schoenholtz, they noted this scale. They didn't note that there's this extra piece here, so that actually it's not a condition for any nearby signals. The way they're perturbed has to be orthogonal in order for the scale to be the scale. But assuming you restrict to orthogonal perturbations, you have the scale. Okay. So if we set m equals to 0, or we let this scale diverge, or sorry, we let this quantity go to 0, or let the length scale diverge.
Go to 1 again.
Sorry. Yes. Set this to 1. Set this to 0. That's what I mean. You can use this to define a length scale which diverges, which is how they talk about it in their paper. Thank you. But if we define these orthogonal perturbations to be massless, then nearby inputs that are orthogonal will have their distances preserved. And this is reported as sort of a nice condition that you might want so that your network has a chance of propagating signals through the network without information being destroyed. However, there's another condition to consider. When did I start?
So 9 for 8 more minutes.
Okay. Great. So there's another condition to consider, which is a perturbation that's normal to the original input image. And if we consider that perturbation, then we have a different equation to solve, which is delta k at L, L plus 1 equals delta k at L times chi parallel at L. And this similarly gives us an equation for RL that it goes like e to the minus m parallel times L. So it decays exponentially with some mass m parallel given by minus log chi parallel. So there's actually another perturbation, a second independent direction that we could have perturbations, and there's a different scale. The scales are given by this is chi perp, this is chi parallel, and so if we want our signal's norm to be preserved and not decay, then we also need to set this mass equal to 0. So that is the condition is we want to set if we want our network to preserve both norms and distances, then we want m parallel and m perp to be set to equal to 0. And this is I think, akin to a conformal fixed point. So before we just had a Gaussian free theory, but now we actually have a theory where our signals, where these scales are gone. And so this condition was written down in the paper by Schoenholtz and Poole, but they said that you can never satisfy this condition, or but actually that's not the case, and I'll probably just have time to explain how this works. So to solve this recursion, we have CW and CB and K00, or in terms of, sorry, let me say that differently. In choosing our architecture, we have CW and CB, and we have two conditions to satisfy, which is that M parallel equals 0 and M perp equals 0. So the solutions, in principle, should be a point. And we can use these equations to see that in order to set M perp equal to 0, that implies that we need to set our CW equal to 1 over psi prime, the expectation value of psi prime. And since this is true, this will be true at any layer. Sorry, psi prime squared. Similarly, the condition for M parallel equal to 0 is going to give CW equals a different condition. And the condition for both perturbations to be massless is or for there to be a critical point is the following condition. The reason this was missed in those previous papers is that for ReLU and tang, it's somewhat degenerate. You have to look at other activations in order to see how this works more generally. But in general, you can, and I think it's useful in terms of initializing your networks for this to make sure that your activation satisfies this condition. This is that at a particular layer, doesn't matter, you need to have that the activation's correlation with the second derivative of the activation over the derivative of the activation, squared, that goes to 0. And I can't, this is sometimes singular such that you can't, or vanishes, so you can't simply eliminate this condition. You have to consider this together. And one of the things you can do with this is ask what are general properties of this function sigma that satisfy this. Those might be nice activations to use in your network. Another interesting thing, I guess I'm running out of time, so let me just read some interesting things. So for ReLU, you can solve these equations. You get CB equals 0 and CW equals 2. That's and that happens for any kernel. So that's a special property of ReLU, and that sort of goes along with what we think for ReLU initializations. For hyperbolic tangent, we get that CB equals 0 and CW equals 1, and the kernel must vanish. And so that's a singular limit. And that is slightly different than I think what's used in practice for initializing tang networks. It's also interesting that for ReLU, it doesn't depend on the kernel, but it does for tang, and it's possible, and it's possibly interesting that this has something to do with the behavior of tang versus ReLU. I think something even more interesting is that for soft plus, there's no solution to these equations. And so I've wondered, maybe someone from the audience can tell me why soft plus doesn't seem to work as well as ReLU does. Somewhere I read online that it had something to do with it's easier to compute the derivative of ReLUs than soft plus. That really didn't make sense to me, but it seems like why not smoothing it out should make it better. But it so happens that while ReLU has an entire critical line of solutions, soft plus has no solutions. A related thing that mocks up the ReLU, the GELU, which is used in the BERT paper, has two solutions. One is stable and one is unstable. And it predicts slightly different values for the bias and weight initializations. And so that's one thing to check, is see whether those actually perform better.
Can I ask a quick question?
Yeah.
For a linear function, this is always true.
Yeah.
So What does this say? Basically,
Says that they're massless.
they're massless.
In this sense, they preserve distances. I mean, so I had to go fast when I was solving the recursion, but essentially there's some k star that you're perturbing around, and you're considering either perturbations that are on that sphere and nearby, or perturbation off the sphere. Those are the parallel and perp directions, and so ReLU always ensures that those distances get preserved. I mean, sorry, deep linear always ensures that they get preserved. It doesn't mean that they're nice for other reasons. It's just that they let these signals. Right, and that's not surprising because we don't expect that signals fail to propagate in deep linear networks.
But it can diverge.
What?
But it's easy to diverge. If you multiply the signal with a big number, then.
Sure. Well, this is a perturbative analysis, right? This is for.
Perturbation can diverge. Why does it happen?
Which object can?
Delta x times something times something times
Sure.
something, and then it will blow up.
Sure. Well, I mean, you can check what the results of these recursions are, right? If you know for deep linear, you know how to solve everything. So.
Linear, you're just multiplying Gaussian matrices.
So it's a question of whether CB. It's a question about the CBs and the CWs, right? And
so
sure, I don't disagree with you. I guess I'm out of time.
No.
Two other points. Is that okay? Quick points.
Yeah, sure.
One point is that unfortunately, I didn't cover a lot. You can go to higher order in delta X perturbation. If you go to fourth order, you can actually resolve this, or you can see that the behavior is, so we looked at the behavior of this distance, and here it's exponential. If we said m equals to 0, you can ask what is the subleading correction. It's a power law, which is perhaps what we'd expect. The exponent of the power law is 1. One of the things we expect when we return to this using the finite end, finite width analysis is that we get some non-trivial exponent, and one might expect that that would allow you to ask questions about how that exponent is affected by the properties of the network, and that might be something you can design around. There's a lot I didn't get to talk about the finite width corrections and how the finite width would affect all of this, but this is, I guess, sort of at least an intro to the program. Yeah, I guess the final point is some of what I hope this can go towards is that in the end we're able to get better and better estimates of either what these kernels are or what the priors are for these neural networks in a quantitative way that we can continue to improve. So given that we can do that, we can start to ask some quantitative questions about inductive biases or priors, given that we're computing it exactly in this limit. And please talk to me after. There's a lot more I can tell you. Thanks.